Chapter 4 is going to be looking at different types of chemical reactions that occur in water. Now there's actually a whole lot of information in this chapter. It's going to be really important that you keep up with your notes, that you're taking good notes, that you're practicing and trying the problems. Otherwise, this is going to be a very, very hard chapter, okay? So when we talk about reactions that occur in solution, there are some words we need to know. The first word we need to know is solvent. Solvent is the dissolving medium. So it's what we're going to be dissolving our stuff into, okay? So when we're talking about aqueous solutions, which all of the reactions we're going to be looking at in this chapter are, water is going to be the solvent. So we're going to dissolve something into water. Now it's important to remember that whenever I use the word solution, a solution is a homogeneous mixture. So it looks the same from top to bottom. There are no chunks, there are no layers, and it has the same properties from top to bottom, okay? Now when we talk about water, water is a polar molecule. Now what that means is oxygen has a partially negative charge. If we look at our water molecule over here, here's my oxygen atom. That little funny shaped S with the negative next to it, that's telling me that it's a partially negative charge. The reason it has a partially negative charge is that the oxygen is better at pulling on the electrons than the hydrogen is. And so it has ownership of more of the electrons than hydrogen in the shared bond. So it's partially negative, not completely negative, because it's still sharing those electrons. It's just sharing those electrons unequally. So oxygen is partially negative, hydrogen is partially positive, because it's getting those electrons pulled away from it, okay? So this creates the polar molecule because one side of the molecule is negative while the other side is going to be positive, okay? So when we talk about dissolving things, we'll often use the term hydration. And what that is water molecules are actually surrounding the molecules or the ions that we're dissolving into it. And the positive ions in our water molecules are positive ions are going to be attracted to negative oxygen in our water, while negative ions will be attracted to the positive hydrogen side, okay? So here's what it would look like. Here's my ionic compound, ammonium nitrate, NH4 plus is one polyatomic ion, NO3 minus is another polyatomic ion. When I take the solid, it dissolves in water and it breaks apart completely. Now remember, dissolution is a physical process, not a chemical process, so it's not actually reacting with water. That's why the water is above the arrow, okay? But it's going to break apart completely into these ions. Now I've got these positive NH4s. Those will be attracted to negative oxygens in the water. I've got these negative NO3s. They're going to be attracted to the positive H's in the water, okay? So my cation is the NH4. The cation has all of the oxygens facing towards the positive. The anion, the negative ion, NO3, has all of the H's facing towards it in the water. And the water molecules surround each of those ions so that they're no longer in contact with each other, okay? Now, solubility is the ability of a compound to dissolve. Some ionic compounds dissolve better than others, and even then the solubility depends on our solvent. In this chapter we're going to be looking at water, but that won't always be the case. Now it's important to remember that when we talk about solubility, like dissolves like. So water is a polar solvent it wants to dissolve either polar solutes or ionic solutes, because the polar solute will also have pluses and minuses. The ionic solute will have pluses and minuses. So the pluses and minuses here will partner up with the pluses and minuses here. If I have a non-polar solvent, everything shared equally, it will only dissolve non-polar solutes. Okay? Because it doesn't have plus or negative sides. It doesn't want anything around it that has positive or negative sides. It wants things that are also neutral as well. Okay? So, let's talk about electrolytes. Now, you've probably heard the term electrolytes in commercials for Powerade, Gatorade, things like that. Okay? So, what's happening is we're going to talk about how electrolytes form, or what electrolytes are. So we're going to be looking at when the solute is dissolved and the solvent is water. Okay? So we're looking at when something dissolves in water. Okay? I can have a strong electrolyte. Now, when we talk about electrolytes, electro as in electricity, they're going to conduct electricity when we dissolve it in water. Okay? So here we've got our picture, and it's kind of hard to see because it's black and white, but a strong electrolyte is going to light up this light bulb really, really well. Now, I can't just stick in the light bulb into the water with the solute in it and it'll light up. I have to have some sort of power source. But what this does is it allows the power source to travel between the two prongs. My solute has these positive and negative ions, and then the electric current can travel. So the electrolyte does not produce electricity. It conducts electricity. Okay? Now, if I look at a weak electrolyte, again, it's kind of hard to see with the picture, but I'm going to get just a faint glow. It's only conducting a small amount of electricity. Some, but not a lot. So my light bulb lights up, but barely. Okay? If I have a non-electrolyte, when I dissolve it in water and I put my light bulb in the water, nothing's going to happen. It does not conduct electricity. Okay? Now, how well it conducts electricity depends on the number of ions that are present in solution. Okay? My strong electrolyte is going to need to be completely ionized. Now, what that means is it breaks apart completely. Remember, we said solubility was how well something dissolves. Not all ionic compounds dissolve completely. To have a strong electrolyte, my ionic compound has to dissolve, and it has to dissolve completely. Okay? 3 types of strong electrolytes. Soluble salts, so completely soluble, strong acids, and strong bases. Not all acids and bases are considered strong. Okay? When we talk about acids, if they are an Arrhenius acid, which not all acids are, and we'll talk about different definitions, produce hydrogen ions, H+ ions. This can also be called a proton. Okay? The reason it's called a proton is a hydrogen atom is 1 proton, 1 electron. If it has a positive charge, it lost its electron. The only thing that's left is the proton. Okay? So here we've got our acids. Again, we can recognize an Arrhenius acid because it always starts with an H. It's going to ionize in water. It's going to produce an H plus ion and then something else that has a negative charge. If there is a single H in front of my acid, I call it a monoprotic acid. If there are two, like H2SO4, I call it diprotic. And if it had three, I would call it triprotic. H3PO4 phosphoric acid has 3 H's. Okay? A strong acid is going to ionize or dissociate or break apart completely. There are 7 strong acids that we need to memorize. HCl, hydrochloric acid. HBr, hydrobromic acid. HI, hydroiodic acid. HClO4, perchloric acid. HClO3, chloric acid. HNO3, nitric acid. And H2SO4, which is sulfuric acid. Now, it's important to remember with sulfuric acid, even though it's diprotic, when I say it breaks apart completely, it's only that first H plus that breaks apart completely. The ion that forms is HSO4. HSO4 is also a weak acid, but it's weak because it does not break apart completely. Okay? An Arrhenius base has an hydroxide ion, OH-. Strong bases are considered strong also because they ionize or dissociate completely. It's important that you know what your strong bases are. Your strong bases are always going to have an OH ion. They're going to be our alkali metals. So everything in that first group except for hydrogen. They're also going to be our alkaline earth metals except for beryllium and magnesium. So from calcium down. And they will have to be partnered up with OHs. So NaOH, KOH, CaOH2. SrOH2, but they'll be partnered up with a hydroxide ion. Now you need to know your strong acids, you need to know your strong bases, and you need to know that the reason they're considered strong has nothing to do with how dangerous they are. It only tells us that they break apart completely. Strong acids and strong bases are good electrolytes, strong electrolytes.